What is the key idea of the paper?
So in this paper, we revisit the classical idea of a generic camera representation parametrized by the rays, and we apply this to the task of pose estimation from sparse views. And to predict this representation, we propose a diffusion-based model that predicts this representation probabilistically.
Welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. We host early career academics and PhD students to share their cutting-edge research in computer vision, machine learning, and everything in between. I'm your host, Itzik Ben Shabbat, a researcher by day and podcaster by night. Let's get started. Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. Today we will be talking about the paper Cameras as Rays, Pose Estimation via Ray Diffusion. This paper was accepted as an oral to ICLR 2024. I am happy to host the first author of the paper, Jason Zhang. Hello and welcome to the podcast. Can you introduce yourself?
Thank you, Itzik. My name is Jason. I'm a fifth-year PhD student at Carnegie Mellon, advised by Professor Deva Ramanan and Professor Shubham Tulsiani. During the course of my PhD, I've really been excited about how do we create representations of 3D that can be done from very sparse views in the wild settings. I think the goal of my PhD is essentially, if you give me a Craigslist listing or an eBay listing where you have a couple images of an object, how can we still get meaningful 3D representations out of it, despite the fact that we might only get 2 or 3 views of the object that we're imaging?
Wow, super interesting topic. And in this paper, who are your co-authors?
Yeah, so I've been very blessed to have wonderful collaborators. So with me, there's also Amy Lin, my co-first author. She's currently an undergrad. She'll be graduating soon. There's also Monish and Betty, two former master's students at Carnegie Mellon who recently graduated as well. And of course, my advisors, Deva and Shubham.
Wow, amazing. An undergrad as a co-first author. That's nice.
Yeah, she's done lots of fantastic work in the area of pose estimation. How do we learn 3D representations and so on? So definitely follow her work. I'm sure she'll have lots of wonderful things to in the future as well.
Yeah, definitely. All right. Let's get to it in a TLDR kind of format. What is this paper about?
Yeah, so I think typically when we think of a camera, we normally think of it as parametrized as an intrinsics and extrinsics. Maybe we revisit our old classical computer vision textbooks. But instead of representing it this way, there's some generic representations. If you look at like what Sri Nair had been working on back in the early 2000s, he had this idea of a generic camera, where instead of representing it compactly, you can actually represent it as a single ray that passes through every single pixel in the image. And so we're basically just applying this old representation, but for the task of sparse view pose estimation. And when you work on sparse views, there's lots of challenges. One of the biggest being that there's ambiguity. You might only look at 2 images of an object. They might be on complete opposite sides. And so therefore, like there's some uncertainty in terms of predicting where the image is actually being imaged from. And so as a result, we want to be able to model this probabilistically. And what we found was that predicting this using a diffusion model is a really elegant way of handling this uncertainty. If we think of the bundle of rays as just this like H by W by 6, because each ray has 6 dimensions, you can almost think of this as like a conditional image generation model to just directly predict this ray representation.
Wow, okay, that's super interesting. But just to make things clear for the listeners, right? What is the specific task, right? What is your input and what is your output?
Yeah, so what we're considering right now is, for the purpose of this paper, is sparse view pose estimation. So the task will be, we'll come in, take in a couple images, let's say 2 to 8 different input images of, let's say in this case, it's an object-centric setup. So 2 to 8 images of an object. And our output that we want to be able to give is still the camera extrinsics and intrinsics. But the way that we'll do this is we'll first train a network that will predict rays. And from the rays, we will then extract the intrinsics and extrinsics, which we can talk a little bit more in detail about.
Right. So basically in your setup, right, you don't have a video or something like that. You have an object, someone put it on the table or on the floor, whatever. Then he went with his camera, he snapped a photo from here, snapped a photo from there, snapped a photo from another place, had somewhere between 2 to 8 images. This is why it's sparse, right? It's only
Yeah.
2 to 8. It's not very dense in that sense. And what you want to get is basically the camera parameters, right? Where is the camera? What are the intrinsics of the camera, and so on. Right?
Exactly right. Yeah. And what makes this task so challenging, I think, is the fact that when you have very sparse views, the baselines are really wide. So typically you would think of a camera pipeline, something like call map, structure for motion, where you would compute correspondences, estimate a fundamental matrix, run bundle adjustment. But here, if you're taking images that are from very sparsely sampled viewpoints, maybe they're on opposing sides, there simply isn't any area on the images that have any overlap. And as a result, you can't rely on correspondences, which is why we rely a lot on these like data-driven priors about what do objects generally look like, why these learning-based methods have really been the predominant way of doing this task. But yeah, this is the fundamental challenge of how do we get camera poses from these sparse images.
Right. But why is this an important problem? Right? When do you need the camera pose?
Yeah. So that's a great question. And I think like it turns out that like basically doing any type of 3D, the number one bottleneck is actually getting those camera poses. If we think about nerf reconstructions, the first thing you do before you train any nerf is you take your video images, your frames from the video, you run them through call map to get all the camera poses, and then you'd probably even run an undistort function on call map to get them into pinhole so that they're like nicely formatted camera poses that you can train a nerf on. And so what that means is like any nerf that we see, we actually only see the nerfs for which call map was able to successfully get a set of camera poses. And that's not just true of nerfs, right? Like we also have other 3D reconstruction methods, in particular ones where maybe we want to have like maybe like SDF-based representations. Maybe we want something that can get 3D from just like 20 different viewpoints. The first thing that you do is typically to build some kind of camera pipeline and use that as the initialization for any downstream 3D. So in that sense, I think that getting the camera poses is actually one of the fundamental challenges for 3D computer vision. I'm particularly excited about this sparse view setting because I think there's so much data available that is much easier to collect sparsely. So for example, if you imagine you want to build a 3D reconstruction of a building, the easiest way to do it is just take a couple images. Maybe we want to be able to do very high scale, large scale 3D from marketplace data. There, your images are going to be sparse. So I think this type of setup is really nice for getting high diversity, but also for some 3D reconstruction tasks, the only way to feasibly collect data is in the sparse setting.
Yeah, that's like, this is why I think like it's a really important problem to work on, right? Because like you said, all of the nerf papers that we've seen so far, they all rely on this particular point that you have a good camera estimation. And if you have a dense, right, maybe it's good enough, maybe it's pretty good, but when it gets sparse, when you have fewer images, then those fail, and you basically can't do a nerf reconstruction, right? So
exactly.
You're kind of attacking this bottleneck, like this point in the pipeline that fails, and you're making it work, and that's really cool.
Thank you. That's exactly the goal of like why I've been so excited about this area is like there's this tiny little bottleneck that is like forcing all these reconstructions to only look at dense settings. But if we can fix this, now we can actually really create generalized 3D reconstructions pipelines.
That's really nice. And if we're talking about nerfs, right, there are a bunch of nerf papers that try to work on doing it from sparse views, but not from this angle, right? They try to improve the representation. They try to do a bunch of things, right? We even have had on the podcast where they try to attack the problem of sparsity by kind of figuring out those better correspondences and getting better representation, but they didn't attack it from the camera viewpoint angle, but from a different angle. So this is a very interesting direction this paper took. But just to pinpoint, like if you had to say what are the main contributions of this paper, what would be the answer to that?
Yeah, so I think the main contributions are two different things that we do. So the first is we swap out the typical camera representation with this ray-based representation. And so now everything that we predict is basically this bundle of rays. And second, instead of just directly regressing these predictions, we show that diffusion models, conditional diffusion models, are a really effective way of predicting these types of rays in a way that allows you to handle multimodality and predict it probabilistically.
Okay, cool. Super interesting. I can't wait to dive in. But before we do that, let's talk a little bit about related work. Which 2 or 3 papers should people read before coming to read your paper?
Well, I don't know if I can limit it to just 2 or 3 papers. I mean, like, our work really stands on the shoulders of lots of papers. I think maybe the most direct inspiration for a paper was from CVPR a couple years ago called Why Having 10,000 Parameters in Your Camera Model is Better Than Having 12. And the thesis of the paper is essentially that for the purpose of that if we just use our normal camera representations where we have an intrinsics matrix and intrinsics matrix, it turns out that these aren't actually perfect models. They produce a lot of bias, and that you can get a much more accurate calibration basically by significantly increasing your camera parameters. And then, of course, like, our representation really fundamentally comes from Grossberg and Nayar, who led this pioneering work of creating these generic camera representations that just consist of a set of rays. And maybe, at least for the task of sparse view pose estimation, I think our work really follows the paper Pose Diffusion. So this is from Jianyuan Wang at VGG in Oxford, where basically they train a diffusion model for the purpose of sparse view pose estimation, but directly on the rotation and translation of the cameras themselves.
Right. I'll make sure to link those papers in the description. Super interesting works. Definitely worth a read regardless, right?
Yes, absolutely.
But okay, let's dive in. I can't wait. So what did you do and how did you do it?
Yeah, so first of all, so what makes this task difficult, of course, is we need to be able to model uncertainty, and we can't rely on correspondences, so we want to train something that is learned, something that can take advantage of a data prior. So our representation is to use a bundle of rays. Basically, we have a ray that points from the camera center through the pixel, the patch center of every patch of the image. And what's really nice about this representation is we can convert seamlessly between like the generic camera representation with the traditional classical representation, right? Like you can just unproject the rays to get the bundle of rays. And then when you have the bundle of rays, you can use least squares essentially to solve for the camera center as well as the rotation and intrinsics of the camera poses. What's I think really nice about this representation also is that it allows you to model any type of camera model seamlessly. Like, it doesn't matter if you have a pinhole camera, maybe you have a fisheye camera, maybe you even have a camera that doesn't have a camera center, like a cat dioptric camera, or even an orthographic camera. It doesn't matter what kind of representation you use. They can all be, you can just always just train this model with this representation, or just directly predict the rays. So the way the model works is maybe we'll first start with like a regression-based approach. So you can imagine.
Before you dive into that, let's get the representation down first. Okay, this was like super quick even for me. Okay, so you're saying that you have rays. How do you represent those rays? Like, what is it's like a 6-element vector, right? What does it contain?
Yes, fantastic question. So we normally might think of a ray as like consisting of an endpoint and a direction, O and D. So we actually parameterize rays as Plücker coordinates. And so instead of using an origin, we use a moment. And the basic idea, the basic intuition for it is like twofold. So one, the reason you want to use these Plücker coordinates is that now you're not dependent on where the ray passes through. Like, it's it's agnostic to which point you decided to be the endpoint that your ray is coming from. And the second nice bias of Plücker rays is that finding the distance between two rays becomes a really easy geometric operation. This type of representation, I think, like, I first saw it in the light field paper by Vincent Sitzman, but it's really like an age-old idea. Plücker coordinates have been around since the 1600s. I think in our case, maybe they're actually, at least for pinhole cameras, maybe there is a very obvious endpoint that you should use, maybe the camera center. But I would still think that it's still helpful to have this bias that you can with very simple arithmetic operations, find the distance between two rays. For example, when you're reasoning about correspondence and stuff, this type of bias is really useful. So basically, our representation that we're trying to predict is given an H by W by 3 set images, a set of them. For each image, we want to predict like an H by W by 6 set of rays, where each ray has 6 dimensions.
Right. And I have another question. It's maybe it's a little more technical. Like, so you have a bunch of images, and you said that your method is agnostic to the type of camera that it is. But do you assume that all images were taken from using the same camera, or you can like combine like one image is from an orthographic camera, another one is a pinhole camera.
Yeah. So we definitely, the method doesn't make any assumptions that all the images have to be taken with the same camera. In fact, for training our network, all we take in is like the ground truth is just a bundle of rays. It doesn't really matter if that bundle of rays came from pinhole camera or fisheye camera. It just, as long as you have a bundle of rays that is matched with the image, that's all we need to train it. So yeah, there's no assumption about what camera model is being used to image it. But for the purpose of this paper, everything was a pinhole camera, but we were looking at follow-ups for what you can do with not just pinhole cameras, but also fisheye cameras or other camera models as well.
Yeah, I think like if you think about kind of applications, right? If you have like I don't know, like a drone or something like that that takes a picture from so far away, it's almost orthographic, right? So
yeah, exactly. And I think like we don't think about this very often, but most images, like all images that we take, actually have distortion. If you take your iPhone, probably the first thing you might do is press the 0.5x zoom, and that actually adds distortion to the images, right? So like the images that we actually are looking at do in fact have distortion, whether it's natural or just because we like wide angle. We just prefer wide angle footage.
Right. Okay. So let's talk about the regression, right? You have your representation, you have your arrays. What do you do with them?
Yeah, so imagine, let's start with maybe, what is the simplest possible way that you would predict these types of representations? So basically, you can imagine our input being multiple images of the same scene. So we have like n images, h by w by 3, right? You pass them in, and basically we'll extract spatial features. In this case, we use a Dino network to get spatial features. And then basically, we just put this through a transformer who takes in the n by h by w tokens, and it outputs n by h by w rays, where each ray is the 6-dimensional Plucker coordinate. And so now, yeah, the simplest possible thing is just you take a transformer, input is spatial tokens, output is just going to be a ray for each of the patch. And we actually found that this regression-based approach already worked pretty well. We were actually pretty surprised that this thing trained pretty efficiently and could give pretty good results. But of course, the big bottleneck is still that given an image where the object might be very symmetric, you're still forced to commit to a single mode. The network can only output one prediction. And so, so if we just want to modify this regression network for the purpose of diffusion, it actually is pretty straightforward. You can imagine now this exact same architecture, except now we want our transformer to be conditioned on a timestamp for where we are in the diffusion process. And then also we want to condition it on the noisy ground truth ray. So basically, instead of just taking in an h by w by 3 image, we would also concatenate this with the noisy rays themselves. And so with that, otherwise we can still recycle the same assurance you heard before and just use this but for the purpose of predicting a diffusion network.
Right. And like, how do you train this? Like you have the ground truth rays basically, and you basically do this kind of reconstruction loss, right?
Exactly. So we just use standard like diffusion training. Basically, what you would do is each iteration of training, you randomly sample a time step. You use that time step to add some amount of noise to your ground truth rays. And now the network's job is to undo that noise.
Right. Maybe it's also important to mention that how do you get the ground truth rays? Basically, the Plucker coordinates and the like traditional intrinsics, extrinsics are kind of interchangeable, right? You can go analytically from one to the other.
Exactly. So yeah, so because in our data we have images associated with ground truth poses, in this case in the classic K, R, and T format, we would just construct a camera, unproject like a grid of points that corresponds to the center of every patch. And basically from that, we would just get an array that we can compute using Plucker coordinates. Yeah, and that's the ground truth.
Right. Okay, are we done with the pipeline? Like,
yeah, I think it's very simple. Like that's basically it. And then of course, like once you actually predict arrays, we just do some least squares to find the extract back the intrinsics and extrinsics in the representation that is probably more useful, right? So camera center, you just find the point that's closest to all the rays. To solve for the rotation, you basically just find how do you align these rays to an identity camera, so a camera that has an identity rotation matrix. And then to get the intrinsics, for instance, you can just do a least squares optimization over the spread of the rays. So the wider the spread of the rays, that means that the focal length should be smaller.
Right. And like, do you basically train it for, so I guess my question is more about how does it generalize, right? Like, do you like have a training set and then a test set, or does it just do you train just for a specific scene? Like, what's the setup like of
Yeah,
that?
yeah. So for our setup, we basically train on the common objects in 3D dataset. It's a really big video data set of turntable sequences of people going around, let's say, an object and imaging it with a video. And so for the purpose of testing things like generalization, what we do is we only train on 40 out of the 50 categories, and then we evaluate on the 10 held up object categories. And so we find, yeah, the generalization there is generally pretty good. Like even for object categories that you've never seen before, you can still get good quality poses from it. I think the real test of generalization is actually we then go out and take images of objects in our own daily lives, things that are not just in that are just not even in the distribution of the objects in the data set. So for example, water bottles or like printers, or like we had like a mail, like we went to like USPS mailbox, took some pictures of that. And I think there we really show that this doesn't just work on the coded 3D distribution of images, but on even like real world scenarios, real things that you would want to image, and those you can still get good quality poses out of.
Right. We kind of started talking about like results and evaluation, but so let's kind of continue that momentum. But I guess my first question in that regard is how do you evaluate this, right? How do you get ground truth, or is it just qualitatively?
Yeah. So that's a good question. So because in the data set of Co3D, the sequences actually come from video. Because and so if you have very dense video sequences, then you can actually run CallMap on those images, very dense images, and get very good quality camera poses. So basically, the ground truth is from CallMap itself. Of course, we then subsample the sequence, only take, let's say, like randomly select 4 of the images out of the full 200 images in that sequence. And essentially what we evaluate is how good is the camera pose. And so the way that we evaluate this is we evaluate the proportion of relative rotations, what proportion are within 15 degrees of ground truth. And then we also do this for the camera center. So to evaluate the camera centers, we say we do like a Procrustes alignment to find the best possible scale, rotation, and translation alignment. And then after that, we say what proportion of the camera centers are within, let's say, 10% of the scene scale of the ground truth. And the reason that we do this type of evaluation, like the proportion of correct poses within a threshold, is that I actually think that for downstream tasks like 3D reconstruction, like remember the final goal of getting the camera poses is really to do 3D reconstruction. For most 3D reconstruction tasks, it's actually okay if your camera pose is close to the ground truth, but not exactly on the ground truth. We can still do optimization, like maybe like barf style optimization to get you to the final ground truth pose. What really hurts these methods is if the pose is like completely wrong, like 90 degrees off or 180 degrees off. Then there's no optimization that you can do to get you to the correct pose. So as long as you're within, let's say, 15 degrees or even 30 degrees, it's like good enough. So that's why the metrics are designed this way.
Yeah, that's a really good point, right? Have the metric kind of reflect what you care about, right? Because you could have evaluated the distance, but what does it matter, right? If it's like 1 millimeter away, 2 millimeters away, if the end task it performs the same regardless, then that's the wrong thing to evaluate, right?
Exactly.
That's a really nice point.
Yeah.
And okay, so but in which cases does your method fail?
Yeah, so there's still obviously challenges. So the first I think is that symmetry can still be pretty difficult. Like, just because you can predict multiple modes doesn't really mean that you've solved the task of predicting poses for symmetrical objects, right? Like you can imagine you might still need to sample multiple times, and only half the time might you actually get the correct mode. So there's still some challenge in like did we actually get the correct one, and how do we actually at inference time want to sample 100 times in order to figure out which one is the right one? I think also like things like distribution shifts are really challenging. Like we've trained on, let's say, these types of images, but now I want to still be able to get poses for buildings or like maybe like scene level stuff. And right now there's no real generalization to that. To do that, we'd really need to scale up the type of data that we train on to get to that type of in order to work in those types of setups.
Mm-hmm. And during your experiments, did you have any unexpected or particularly interesting findings?
Yeah, actually. So I think in my case, this is actually one of my first times training diffusion models, and so there were like some weird quirks about training diffusion models. But I think one of the most the challenging things is that normally the literature for diffusion models is really on image generation, where we have lots of good schedulers and things that basically are designed for diffusing images. And with images, in the image diffusion literature, there's big focus on one of the important things that you have to do is scale the images properly. So for instance, with images, you want to make sure that your images are always between -1 and 1. While you're doing the backwards diffusion, you want to do some clipping to make sure that the range of values is always between -1 and 1. But with rays, these types of scale restraints don't come for free, right? Like the directions, will always be between -1 and 1, but there's no reason that the ray moments have to be between -1 and 1, right? And so when you're doing diffusion, not just on this very nice space of image pixels where everything is always between 0 to 255, but rather just some kind of geometry in the scene, suddenly this becomes a lot more challenging. So we had to think hard about how do you scale the scene, normalize the moments, do all these things properly in a way that you can still predict them efficiently. So maybe, for example, some of our design choices were that we want to scale the scene in a way so that the scene is always relatively small, so that you don't get moments that are very, very large, although occasionally you still do get outlier moments that are way outside the -1 to 1 range. Another interesting thing that we found that was a little bit surprising is that, and this is not something I'd seen previously in the literature, which is that at every step of backwards diffusion, you can actually compute the induced x0 prediction. Like at every iteration, you can say based on this current xt, what do you think the final x0 will be? And what we actually found was that the best possible performing prediction wasn't actually the x0 that we got at the end of completely at the end of the backwards diffusion, but somewhere near the end. This was something that I'd never seen before and had never seen anybody discuss before. So if anybody else has seen this, I'd be very curious to hear more about other people's experiences training these diffusion models.
Interesting. Yeah, definitely. If you're watching this on YouTube or on the podcast, leave a comment to Jason and tell us your experience with this. This is really interesting to me as well. I don't have a lot of experience with diffusion models, so I can't weigh in a lot. But yeah, these diffusion models, they're not here for that long, right? So we're still learning them, and maybe there's something there, right? Maybe that's the next research question to answer, why this is happening.
Yeah.
So yeah, I went over the tables in the paper. Obviously, you got all the bond numbers. You're beating all of the state-of-the-art methods, right? You're leaving dust to call map, which is important to mention. But actually, in that regard, it's how do you perform compared to dense methods on dense input? Have you tried that? It's not in the paper, but just I'm curious.
So in the dense setup, I think call map is still a gold standard. If you have sufficiently dense views, you can get very good quality correspondences, and I think PNP is probably just the right way to solve it. I think as a field, we're actually getting to the point where, for the first time, I think linear-based methods are getting very close to the performance of call map, if not outperforming it. But I don't think we're quite there yet. We do have some experiments on how does our performance look if you just increase the number of images significantly. And I think if you look at our tables, you'll see that as you increase the number of images, the performance increases, but it does eventually plateau. So once you increase past 8 images to 30 images, maybe even 40 images, the performance plateaus. Whereas I think call map essentially will give you perfect results if you have sufficiently dense results. In some sense, though, our ground truth does come from call map, so it makes sense that if you increase the number of views, call map converges to the performance of call map. So it's a little bit tautological. So maybe we need another way of getting ground truth. But I do think that call map can give you very good quality poses. It's just that in the sparse view setting, something like 60% of the time, call map doesn't even converge. It doesn't even give you an output model to compare against.
Right. Yeah. And also another experiment that I liked in your papers, you kind of explored the trade-off between computation time and accuracy, where you kind of looked at the patch size, right? You increase the patch size so the performance improved, but that comes at a cost, right?
Yeah, that's exactly right. And with training these transformer models, there is always a big bottleneck because there is like this n squared operation in order to compute self-attention. As you increase the number of patch tokens, naturally you're going to increase your compute and memory cost quadratically. And there are some ways to mitigate that. I think if you look at dense prediction transformers, for example, DPTs style architectures, they have ways of still doing pixel line prediction, but in a way that's not so computationally expensive. And I think going forward, that's another direction to really like scale up the number of rays that you can predict to get it actually to be pixel line instead of patch aligned, but in a way that doesn't blow up your compute. Yeah.
Right. This is actually a great bridge for the next part of the podcast, which is conclusions and future work, which you just mentioned what might be a future work. But so how do you see the impact of the paper going forward? And are there any interesting papers that followed it?
Yeah, absolutely. So I think, well, my hope really for the people take away is for us to revisit these generic camera representations. I think like being able to train on images that don't have to be undistorted, don't have to all be fisheye cameras, allows you to really take advantage of very large scale data without having to pre-process it in a way that actually throws away a lot of the information that was captured. And even during inference, right, like a lot of the images that we take are in fact not perfect pinhole camera. So I think one of the things that we've been looking at is how do you really, how do you use, like any type of camera model and train with a single image using any camera model, but train it with just this generic representation. And of course, like this follows like a long line of work, mostly in the calibration space. But for example, there's a paper called Neural Ray Surfaces that also has explored like how do you predict pose in this like with this generic camera representation. I think concurrently to our paper, there's like two other papers that actually have very similar ideas. So the two papers are PFLRM and Duster, and both these papers came out pretty close in time to when our paper, when we first submitted it to ICLR. I think PFLRM is actually also an ICLR paper. And in both of these papers, really the idea is that for every pixel, instead of predicting an array, you want to predict a point, a 3D point in the world. And then from those 3D points, you can use PNP to solve for the camera pose afterward. And so in that sense, it's actually really similar to our paper. Instead of predicting array, it's just predicting a point. But the final way that you get the cameras is essentially the same. You just use classic optimization-based approaches. In particular, I think what Duster did that was really cool is that they show that if you just train on lots and lots of data sets, if you really scale up to scene level data sets and self-driving data sets and basically every single data set that you can get your hands on, you can get excellent quality results. And if you like look into their paper, I think they can get really fine-grained geometry, really good quality camera poses from just doing this type of point cloud regression given pairs of images. And I think in some sense, like this is kind of like the direction that the field is headed towards. Of course, I think they came at it from a very different perspective, maybe from the SFM style perspective where you want to get the geometry. We came at it from the perspective of camera arrays, but in some sense, like these are come hand in hand. If you want to convert array into also getting geometry, of course, you just predict an extra parameter, an extra depth parameter, and now you've predicted both the ray and the 3D point in the scene. So I think this is just the direction that hopefully the field will be headed, is just like this very dense geometric prediction, after which you use PNP or classic optimization to solve for camera poses.
Wow, super interesting. Yeah, I'll make sure to check those out myself. I'm a point cloud person, so I find that interesting.
I think this is just super cool that like, and I think this is like what it'll take for learning-based methods to really catch up to CalMap. In some sense, it's predicting, like these methods are directly predicting 3D correspondences from which you can still do bundle adjustment style or PNP style optimizations. And I think, so this is what I think it'll take for us to really close the gap to these classic optimization-based methods for getting camera pose.
Cool. Yeah. Okay. So I think that's an excellent direction to go to, right? If PhD students are kind of thinking what are interesting problems to work on, here you go, right? This is like a nice direction to head. Okay, we're getting to my favorite part of the podcast. What did reviewer 2 say? Can you please share some comments that the reviewers had in the review process?
Yeah, absolutely. So I think, well, first of all, the paper is an ICLR paper, so publicly available. You can check out the open reviews that the reviewers had and the discussion that we had with them. I think the overall takeaway was that the reviewers were excited by the type of representation that we're doing. Like the idea was clearly new and applied to this task for the first time. Of course, we also had the diffusion model and showed that diffusion modeling in probabilistic is helpful. Over parameterizing your camera arrays is helpful. I think the main complaint, especially from R2, is really that like we need to demonstrate it on more data, and I think that's a really fair complaint. I guess as a person who, for the entire PhD, has been working on how do we solve the Craigslist task, I think I'm really interested in this object-centric setup, right? Like where we take images of objects, go around this object, and then be able to get 3D representations out of it. But to really have the type of impacts that I think things like systems like CallMap, or to really make it so that every nerf will just, instead of using CallMap, use this system, I think you need to scale up on more data. And so in that sense, I think R2 was right. And I think that was what I really took away from the Duster paper as well, is that by scaling up to lots of data, you can really get good quality geometry, good quality poses, and so forth. So in that sense, I think that's something that we are also thinking a lot about, is like, how do we put in the that it's necessary to put in the engineering effort to really train on every single data set, train on every camera model that you can. And I think that's what it'll take to really get this type of work to shine. So in that sense, R2's complaints are really well taken, something that we are absolutely working on. But but definitely at the time, there was a lot of back and forth about like, what can we feasibly do during a rebuttal period in terms of training it on a new data set and evaluating on scene level data sets and so on. I guess some other minor criticisms might be things like the heaviness of the method. So typically, if you predict a camera, you would only have to predict something like 12 parameters, right? But in our case, because we're predicting an array for every patch, if you have 16 by 16 arrays, now, and each array is 6 degrees of freedom, suddenly you're predicting 1,500 parameters instead of just 12 parameters. So in that sense, yeah, the representation is a little bit more heavy, but I guess if you just think of this as being the last layer of the network, I don't think it actually adds that much compute. And I also think that this type of overparameterization does significantly improve the performance, and so I think it's worth justifying the extra computational cost of doing this.
Right. Yeah, and it's always like, this is the nice thing about doing research, right? Like you can just say limitation section, right? A lot of compute, and you're done, right? But where, a lot of times, like you ask, okay, so how do we bring this to the world? But maybe that's a different research question, right? Like, how do we implement this in a product? But yeah, maybe that's a different research. How can we make it more compact or smaller or more efficient or whatever? And these are two separate research questions, right? Here you brought the Plucker representation with the diffusion model, and you created something that didn't exist before. Amazing, right? This is the first step in that direction. And then maybe the next step is, okay, let's make it more, I don't know, fast, efficient, whatever, right? It doesn't make the paper not as good, at least as far as I'm concerned, but it's a valid point from the reviewer side, right? That this point should appear in the limitation section or whatever.
Absolutely, yeah. And I think we're seeing ways that we can speed this up a lot. Like, for example, with diffusion, there's lots of tricks to making the backwards process a lot faster, whether it's like DDIM inference or DPM solver. Like, there's lots of different approaches that we didn't even have time to look into, but could definitely improve the inference speed out of the box. But yeah, hopefully in future work, we can have very fast inference, very accurate inference as well.
Yeah, when people talk about speed, I always remember that during my PhD, I had a 1080. Right, that was the latest thing, right? The 1080 GPU. This is what we ran on, right? So today, right, everything seems like, speed. Tomorrow they have a new GPU that works faster, and then there are a bunch of more tricks that make everything faster. It will work itself out. Right?
That's true. That's true. Yeah, but I guess in some sense, I think what's really nice about this area also is that is to consider this not just the absolute inference cost, but also the scaling laws. So in this cases, by doing like this type of feed-forward prediction, your runtime is really just linear with respect to the number of inputs. So maybe even though right now it's slower than running CallMap on 8 images, but if you really increase the number of images to, let's say, 100 images or even 1,000 images, suddenly the linear compute time versus the quadratic compute time of CalMap becomes a lot more attractive. And so I think like going forward, if we can get to the point where we close the gap with CalMap performance, a big gain that we have, even if we can't close the precision gap, is that the inference speed should be much faster. Instead of waiting 3 days for me to get my CalMap poses, maybe it's just a matter of running it for half an hour or an hour.
Ah, interesting. Cool. Okay, amazing. Listen, I feel like we can keep talking forever, but I think it's a good point to start wrapping up. Anything you want to add before we do?
I guess, yeah, I hope that people like revisit lots of classical old ideas. I think like this paper, like doing this paper, I think made me really go back and like have to like familiarize myself with what people were doing 10, 20, even 400 years ago, and where there were lots of very interesting ideas that we just, I think, like starting when you like start as a fresh-faced grad student, you just don't read those old papers anymore. I think lots of those ideas, they come back and they're very, very useful, that have since been forgotten as like people work on more and more deep learning and like machine learning type research. But in reality, lots of classical applications, classical ideas are actually really important. So I think it's just useful always to revisit old ideas, and often they come back and become useful again.
Ah, that's such a great advice. I totally agree. Like sometimes you have this thing that seems ancient, right? In our days, right? You have a paper that's like 1 or 2 years old. Oh, it's old news, right? But then you read a paper that's 40 years old, has like this nice idea, nice representation, nice thing that they did. You plug it into some new learning-based method, and it becomes this amazing new fusion type thing. So yeah, definitely a great advice. I will also add, by the way, that this paper also has the code available, right? And a very good project page that I really like the animations of how the diffusion model works with all the rays that kind of converge into the camera. So definitely go and check that out. Or we'll put the link in the description. Okay, Jason, it was great having you on the podcast. Thank you very much for being a part of it. And until next time, let your papers do the talking.
Thank you so much. This was a pleasure.
Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.